Hello, fellow technicians. In today's video, we will analyze the engine block and how the ECU controls the engine. Understanding this process will make it easier for you to repair the ECU and the engine's electrical system. The ECU collects signals from sensors, processes data, and controls actuators. This is a crucial process that helps in accurately diagnosing faults and effectively troubleshooting complex issues in the engine control system. If you want to master how this system works and take full control of your repair tasks, make sure to watch this video until the end. Now, let's get started. A car engine is a complex mechanical system that operates by converting fuel energy into mechanical energy to create motion. To fully understand its operation and perform precise repairs, we need to carefully analyze each key component in this system. 1. Structure of the engine block. 1.1 Cylinder block and crankshaft, connecting rod mechanism. The engine block is made up of many components, but the key parts responsible for movement include cylinder. This is where the combustion process takes place, generating power. An engine can have between 2 to 12 cylinders arranged in different configurations such as inline, I, V-shaped V, or opposed boxer. Piston moves up and down inside the cylinder to complete the 4 strokes: intake, compression, power, and exhaust. Pistons are made from aluminum alloy, making them lightweight, durable, and heat-resistant. Connecting rod connects the piston to the crankshaft and converts the piston's up and down motion into rotational motion. Crankshaft rotates to transfer power to the flywheel and transmission. It has counterweights and bearings to maintain balance and smooth operation. Hash 1.2 Valve timing system. Camshaft, intake, and exhaust valves. The valve timing system ensures that the intake and exhaust valves open and close at the correct times, synchronized with the piston's movement. Camshaft controls the opening and closing of the intake and exhaust valves. It can be located in the cylinder head, OHC, DOHC, or inside the engine block, OHV. Intake valve and exhaust valve. These valves work in cycles, allowing the air-fuel mixture into the cylinder and expelling exhaust gases. In some modern engines, the valve system is controlled electronically using variable valve timing (VVT) technology. This helps optimize performance and improve fuel efficiency. Engine operation principle. Internal combustion engines work based on 2 main cycles: 4-stroke cycle, commonly used in cars, 2-stroke cycle, found in some motorcycles and marine engines. The 4-stroke cycle consists of 4 phases. 2.1 Intake stroke. The piston moves downward, creating a vacuum inside the cylinder. The intake valve opens, allowing air or an air-fuel mixture to enter the combustion chamber. In gasoline engines, fuel is mixed with air before entering the cylinder, port fuel injection, or injected directly into the cylinder, GDI, gasoline direct injection. In diesel engines, only air is drawn in during this stroke. Fuel is injected later during the compression stroke. 2.2 Compression stroke. The piston moves upward, compressing the air-fuel mixture. Both intake and exhaust valves remain closed to increase pressure inside the combustion chamber. In gasoline engines, the mixture is compressed to about 10 to 12 bar, preparing for ignition. In diesel engines, air is compressed to an extremely high pressure, 20 to 30 bar, raising its temperature to around 500 to 700 degrees Celsius, hot enough to ignite the fuel when injected. Hot 2.3 Power stroke. In gasoline engines, the spark plug ignites the compressed air-fuel mixture. In diesel engines, fuel is injected into the hot compressed air and ignites spontaneously. The high-pressure combustion gases push the piston downward, generating rotational force for the crankshaft. This is the only stroke that produces power in the cycle. 2.4 Exhaust stroke. The piston moves upward, that's pushing exhaust gases out through the exhaust valve, Freivalve. The exhaust valve opens, allowing gases to exit through the exhaust pipe. If the engine has a turbocharger, the exhaust gases may pass through it to improve efficiency. After this stroke, the cycle starts again from the beginning. 3. Essential supporting systems in the engine. To ensure smooth and efficient engine operation, several important systems work together. These include the fuel system, ignition system, and air intake and exhaust system. 3.1 Fuel system. The fuel system ensures that fuel is delivered at the correct pressure and timing for efficient engine performance. Key components include fuel injector, sprays fuel into the combustion chamber in a fine mist for better combustion; fuel pump, draws fuel from the tank and supplies it to the injectors at the required pressure; fuel pressure regulator, maintains stable fuel pressure, ensuring the right amount of fuel is delivered to the engine. 3.2 ignition system, gasoline engines only. This system is responsible for igniting the air-fuel mixture to generate power. Key parts include spark plug, produces an electric spark to ignite the fuel mixture inside the cylinder; ignition coil, converts the battery voltage into high voltage, 10,000 to 40,000 volts, to create a strong spark. 3.3. Air intake and exhaust system. This system manages the airflow into and out of the engine, ensuring efficient combustion and exhaust removal. Intake and exhaust valves control the flow of air into the engine and the release of exhaust gases. Turbocharger, if present, uses exhaust gases to compress incoming air, increasing engine efficiency and power output. 4. Application in ECU diagnostics and engine electrical systems. Understanding how the engine operates helps technicians diagnose engine faults using sensor data from the ECU. Inspect and repair key components such as camshaft sensors, crankshaft sensors, fuel injectors, spark plugs, and ignition coils. Understand how the ECU controls fuel injection, ignition timing, and variable valve timing, VVT, making it easier to identify faults accurately. In-depth analysis. The role of the ECU in engine control. The electronic control unit, ECU, plays a key role in managing and optimizing engine performance. Acting as the brain of the vehicle, it continuously collects sensor data, processes information, and adjusts various systems to ensure strong engine performance, fuel efficiency, lower emissions. 1. How the ECU works in engine control systems. The ECU uses a high-speed microcontroller unit, MCU, to analyze sensor data in real time. Its operation can be broken down into three main stages. 1.1. Collecting data from sensors. The ECU gathers signals from multiple sensors, including crankshaft position sensor, CKP, measures engine speed; camshaft position sensor synchronizes ignition timing and fuel injection; oxygen sensor detects oxygen levels in exhaust gas to adjust the fuel mixture; mass airflow sensor, manifold absolute pressure sensor, MAP, measures incoming air to calculate the correct fuel supply; engine coolant temperature sensor, ECT, adjusts fuel mixture based on engine temperature. 1.2. Processing data. The ECU runs complex algorithms to calculate and adjust engine parameters based on driving conditions. 1.3. Controlling actuators. Once the data is processed, the ECU sends control signals to various components, including fuel injectors to regulate fuel delivery, electronic throttle to control air intake, ignition system to manage spark timing, variable valve timing, VVT, system to optimize efficiency, turbocharger, if present, to improve power output. By understanding these ECU functions, technicians can diagnose and repair engine issues more effectively. Conclusion. Every sensor plays a crucial role in how the ECU controls the engine. Understanding the impact of each sensor helps technicians diagnose faults more effectively, optimize engine performance, and extend vehicle lifespan. #6. Final thoughts. The ECU is the brain of the engine, managing fuel, ignition, and overall performance. Since sensor signals directly affect engine efficiency and longevity, having a solid understanding of these components makes troubleshooting and repairs much easier. We hope this analysis provides valuable insights into automotive engine control systems. If you have any questions, feel free to leave a comment. Thank you for watching, and see you in the next analysis.